Hi guys, welcome to this video on basically Python tutorial on optimization. And in this first video, we will be looking at a problem commonly known as a knapsack problem. And basically we will look at an example, and using that example, I will try to explain how you can solve these problems and which methods you can use. So the example I want to discuss is basically the example of a fruit importer, or somebody who imports fruits from all over the world. And I've included a table containing a number of fruits that this person might be interested in. And there's kind of a big problem. This person doesn't have a big car. He basically just has like a bag, I guess, and he can only carry 2 kilograms of fruits. And so the question is, how much do we take of each fruit to maximize our profit, right? So if we look at this table, we basically have a selection of 6 fruits. I don't even know most of these fruits, but I guess they might say, they might be really tasty. And what we can see is we can see the weight of the fruit, and we can see the profit per unit. And what we basically want to do is we want to find out how much of each piece of fruit we should take, and we're assuming that we only take whole pieces of fruit, so there won't be any fractions whatsoever, in order to maximize our profit. And there are numerous methods to actually solve this problem. You might have an idea yourself, and there's 2 methods I want to cover in this tutorial. The first method, which is a very simple method, would be a greedy approximation to the problem. And I will discuss what that entails in the next piece. Then we'll also look at dynamic programming methods, and if you're not really familiar with those, it's not a problem. I will first introduce what dynamic programming is, and after that we will look at dominance relations. And that's basically not a solution method, but it's just something I wanted to discuss at the end. So let's look at a greedy approximation. So essentially, if you look back, if you think about the problem we are trying to solve, we have a bunch of fruits with different weights and different profits, and we want to find the best combination of fruits to take. And so a simple solution would be to, initially just take the fruit with the highest profit, but we only take as much so that we don't exceed the weight limit that we have. So in our case, right, the bag is 2 kilograms. So if you look at this table, we could, for example, only buy 1 durian, right? Because if we take 1 durian, then we have about 1.5 kilograms, and we would make a profit of about 22, maybe dollars or euros, whatever your local currency is. And so if you take 2 durians, then you won't be able to satisfy your constraint, or basically satisfy the fact that your bag can only carry 2 kilograms. So let's go back. And basically this strategy is very simple to implement, but it's not guaranteed to give us an optimal solution, meaning that if we take this strategy at a variety of different problems, then we're not guaranteed to find the best set, right? We're not guaranteed to find the best amount of fruits. But that's not necessarily bad, right? Even if it's an approximation, if it's good enough, right, then we can be happy, I guess. So let's now switch over to the editor and actually code up a greedy approximation method to this problem. So this is my basically VS Code editor, standard editor that every developer loves. I will use this editor to code up a greedy algorithm. And I've already prepared the data from the table, and I've put it inside of this list, right? I've made a list of tuples, and you might be like, what is a tuple? What is a list? Well, a list is basically mutable. If I think about it, I could have also made it a tuple of tuples, but it doesn't really matter. It's just a way to represent the data. If you look, the first entry is the name of the piece of fruit, then the profit value, and then the weight, which is given in grams. So 1 kilogram is 1,000 grams if you like use the metric system. So that's one way we could potentially convert our grams and kilograms. So let's actually write a implementation for this first, or basically the first greedy approximation. And I'm just going to define this function, and I'm going to name it greedy fruit. And what should this function take as arguments? Well, of course we should just take the items, and we should take something that I'm going to call the capacity. And so the capacity is the maximum amount of kilograms, or let's say grams, because that would be easier, that we can carry in our bag. Okay, so if we think back, what does the greedy algorithm do? We basically need to find the fruit with the highest profit, right? And one very easy way to do this would be to sort the list which we have based on the profit of each piece of fruit. And you might be like, why should we sort it, right? We can just at every single iteration compute the maximum value, but that would be less efficient, right? If we first sort the list and then we just iterate through it in its order, then we wouldn't have to compute the maximum every single time again. So let's do that. Let's set items, which is basically our list, equal to the function sorted in Python, which we can call to sort a list. And then we pass the list items, which we want to sort. And then as a key, we basically use a lambda function. And the lambda function is basically like a small anonymous function you can call in Python. And oh, I made a tiny mistake here. It shouldn't be there. So it's a tiny function you can call in Python, which allows you to define a function without having to go through the entire define. So it's like a very small operation. So basically this would sort our list in a ascending order, but we want to reverse this. So let's enable that. Let's reverse this list. And basically if we look at this list now, we would have a list of items that would be sorted based on the profit or the value of the item, right? And we can just simply check this if we wanted to see that that does actually happen. So I'll just call the function greedy fruit. I'll pass in items, and I'll pass in our maximum amount that we can carry, and then I'll just run this, right? I clicked it twice, no problems. So if you look at this output, we can see that the values are ordered, and the highest profit, which is 22, which is durian, it's a very expensive piece of fruit, and the lowest, which would be cucamelon, and that would just be 26 cents, or whatever your local currency is. So let's continue. That seems to work just fine. Just going to put this down a bit. Perfect. All right, now we're going to actually start writing the function. And there is a number of things we need to keep track of. And one of those things is we can make it a dictionary or a list. We'll make a dictionary called chosen fruits. And basically, when we're going to iterate through the items, we're going to add a key, basically the name of the fruit, and we're going to add how much of that specific piece of fruit we actually want. So that's why we use chosen fruits. And we will also define another variable, which we call profit. And basically, we use profit to store the total profit of our fruit selection. So let's now start with the program, and we use a for loop, and we are just going to iterate over all of the items or all of the fruits, and for each fruit in the sorted array we are going to have to figure out basically two things, right? We want to know how much of this fruit should we take, And then we want to know how much capacity is left. So let's first unpack the tuple. And so basically what this does, if you're unfamiliar with the syntax, is if you look at this tuple right here, you can unpack this and it would just store the name of the item in the variable name, the value or the profit in the variable value, and the weight in the variable weight. And this makes it easier to follow the code I'll write next. So now let's face our first problem. How do we compute how much we should actually add of a specific piece of fruit? And so basically the question that we're asking is, if we have a given capacity, how many times does the fruit fit in there? And you might be thinking, well, maybe something with a modulo operator can help us out here. And that is correct, because if you want to know the number of the pieces of fruit, basically how much fruit can we buy of this specific item, then we would just take the capacity, which is the current capacity we have in our bag, and we would subtract from that the capacity modulo the weight of our current fruit, and then we would just divide this by the weight. And so this line might be difficult to understand, so let's just do an example, right? Imagine if we were to have a bag with a capacity of 9 and a weight of 2, right? Then let's look at this operation. Basically, we know that this fruit with a weight of 2 fits in here 4 times, right? So let's see if this operation truly returns that number. Okay, so what would be the capacity modulo the weight, right? So the modulo operator returns the remainder of a division. So if you divide 9 by 2, then you would get 9 modulo 2, you would get 1. So the outcome of this operation would be 1. Then we would take 9 minus 1, so we would get 9 minus 1, and then we would divide that by 2. So it's clear that this gives 4, right? So basically this expression right here evaluates to that which we wanted to evaluate to, so it works. Now once we know this, we can basically add or append this to our dictionary, and we will use the name of the fruit as a key, and we'll set this equal to num of typing always remains a struggle, num of fruit. And so now we have basically said for the fruit with this name, we are going to select this much, right? Okay, now let's update the capacity, because we have added fruits. Basically, we have chosen or picked some fruits, so we've put them into our bag. We don't have as much capacity as we did before, so we need to adjust this. And if you think about it, the capacity that's left is just the remainder of this modulo operation, right? That is how much we have not used yet. So we can just set that equal to that. All right, now we have one thing left, because basically everything seems to look fine. We just need to compute the profit we have for this specific selection of fruits we have. So let's say that the profit, right, we are going to add to that the number of fruits multiplied by the value, right? So basically we have selected this amount of fruits, and for each piece we have a profit with the amount of value, and we add this to the total profit. This would be the implementation of our greedy algorithm, and I'm just going to return the rounded profit up to 2 decimal places, just because that looks kind of nice, and the chosen fruits dictionary. All right. Now we could actually run this and see what is the combination of fruits we should buy according to this algorithm or this strategy. And we don't display anything because you need to print it. So it's not the Jupyter notebook. All right, there we go. So we can actually see that the total profit of this selection of fruits is 29.6, and we would take 1 durian, we take no pomelo, or pomelo, I guess, we take 2 avocados, no star apples, 8 lychee, and no cucamelons. So, the question is like, is this truly an optimal solution? And it turns out that it isn't, right? And it's very simple to actually show that it isn't, because we are just going to take this algorithm we have just written right here, and I'm going to duplicate it. You might be like, why are you going to duplicate it? Well, I'm going to make a very simple change to this algorithm, and I'm just going to call this the greedy fruit Danzig. And so who was Danzig? Danzig was this guy, this man, and he came up with, a small trick, and we can actually just apply that trick, and that will make our selection or profit a lot better. It still won't be an optimal solution, or it is not guaranteed to be. It could be. And the only thing we do is we divide the item profit by its weight. So initially, when we actually sort this array, right, in this first method, we just sorted it based on the profit, but we didn't look at the weight. But now we will sort it based on this operation here, or based on this. We will sort it based on the profit divided by the weight. And if you think about this, imagine you have a product or piece of fruit, which is like a pumpkin, right? A pumpkin might be, very expensive, so you might get a lot of profit, but it's very heavy. So it would still be a mediocre decision to actually take a pumpkin. But if you have for example, a grape, right? And a very good grape, and from France or something, then even though the weight will be very small, but we would still get a decent amount of money for that one grape. So basically, you need to look at the ratio, or you want to basically take into account both the profit and the weight, and this will actually give us a better solution. So the way we could actually see that is by also copying this, and now calling the second function also. And now we can compare both of these. And now if you look, right, you can see that the greedy fruit Danzig actually produced a profit value of 40, right, which is significantly higher than 29.6. So this was not optimal. And if we look, like, what did it actually take, right? It just took 100 lychee or lychees. I don't know if that's leeches. Not leeches, though. Those are, you shouldn't eat those. I don't really know how you pronounce that, but I guess lychee. So initially, you might be thinking, 100 of these tiny things, it would seem intuitively that you should grab the item with the big profit, like a durian, right? But it turns out that actually that is not optimal. But how can we, know for sure that this thing right here, this 40 that we have, is an optimal solution, right? Because I told you that these greedy methods that we're using, they're approximations. So they don't guarantee that we have the best solution or the best possible combination of fruits. And for that, we will actually use a dynamic programming method, or basically dynamic programming. So I'm going to switch back to my slides. So basically, let's discuss dynamic programming now, and let's discuss how we can actually use this to find a way to check whether our greedy algorithms performed, very well or didn't perform very well. And so dynamic programming is basically a collection of techniques, essentially these 3 techniques that make up a tool set that allow you to create or write algorithms that are very performant and very strong. And the 3 techniques are known as recursion, memoization, which is really a cool word, I guess, and a bottom-up method. And so recursion, you might have heard of that before, and it's basically a concept where you take a problem or a function and you write it in such a way that the function uses itself to solve a problem. So most of the times, where you might have seen this is with a Fibonacci series, right? Fibonacci is a recurrence relation, meaning it's recursively defined. And therefore, if you are to create that on a computer, you could use a recursive function, a function which calls itself to solve the problem, right? But the problem with most of these recursive functions is that they basically recompute values that they have already computed. So for example, the Fibonacci sequence, if you were to imagine this graph, right, this computation graph, you would find that there are values inside of it which it's computing over and over again, which is of course not efficient, right? Which is where the second technique called memoization comes in. And that's basically very simple, but of course also very powerful. You just store a solution when you have solved it, right? So basically you will have these subproblems, you found the solution to them, and you store it in an array or dictionary. And the next time, before you're going to start solving a problem, you're just going to ask yourself, wait, have I stored this? And if I have stored it, then you're just going to use the stored solution instead of using the solution, instead of recomputing the solution. And then the third approach is basically flipping around. Bottom up basically starts at the very base level, at the subproblem, and then you build up your way like a tower towards the actual problem you're trying to solve. And this usually will yield an improvement when it comes to the memoization technique, because of course when you use memoization you have to store these values, right? So it will take up extra memory. With the bottom-up method, most of the time, most solutions, you won't have to do that. So what we are now going to do is we're going to create a basic dynamic programming solution to our fruit problem. And once we have written that, we can actually find out whether our greedy algorithms performed well or whether they didn't find the optimal solution. So I'm going to switch back to the editor again. All right, so let's start coding up this solution. So I'll basically define a new function, and I'll call it dynamic fruit, right? And it's not like the fruit is dancing or something or jumping. It's a very dry joke, I'm sorry. But it's basically reflecting the fact that we're going to use dynamic programming. And basically the way that this function is going to work is it's pretty interesting, right? We are going to look at this capacity of ours, and we're going to say, well, this capacity is a bit too big for us to deal with. So let's just split it up, right? And let's just split it up such that we go all the way to a capacity of 1. And then we're just going to solve the problem for a capacity of 1, right? Once we have done that, we're going to solve it for a capacity of 2, and then for 3 and 4. But we're going to use the solution of the prior problem we solved. And then we're just going to continue with these operations until we are at the capacity or the desired capacity where we start. So in order to do this, we basically need to define a list to keep track of all of these values. I'm just going to call it bag, and this bag it's just going to contain zeros at the moment. And so this is basically a list comprehension, or like a for loop inside of this list. And it's just very fancy notation, but what it actually does is just put capacity plus 1 zeros in this list. Okay, so now let's start actually iterating over all of these capacity values. So for this, we'll use a for loop again, and we're going to iterate over these capacity values. And now we're actually going to start the problem solving part. So we have to check for all possible pieces of fruit whether we can add it in, and whether it's a good thing to add it in, right? So we're going to check for all of the fruits. That's what the second for loop is for. What are we going to check? Well, before we start checking, let's just unpack the tuple again. But this time, I won't be using the name. So I'm just going to use this symbol because I'm not going to use it. So basically now, what should we check, right? Well, what's very important is that when we add in a piece of fruit, we need to make sure that that piece of fruit is not too big, right? Or it doesn't have too much weight so that it's going to basically break our bag. So let's make sure to check that. Let's check if the weight of the fruit is actually less than the current capacity, right? Okay, now comes an interesting line. So if the weight of the fruit is less, right, then there are going to be two options, right? And we're going to pick the best one. And in order to reflect this, we're going to use the max operator, which returns the maximum. And so the two options we're going to evaluate are the current bag and the bag of, basically the bag that we would get if we were to add in this piece of fruit, right? So let's evaluate this line. So we have basically checked for a certain piece of fruit if its weight was less than the sort of semi-capacity or the capacity that will be growing. And then in order to make our decision, do we add it into the bag? We're going to check two things. We're going to check which one of these two things returns the best solution, right? So bag I would just be the bag without the item added in, without this specific piece of fruit added in. And this expression here would be the value of our bag with the fruit added in, right? Because we actually subtract the weight and then we add in the value. So that actually is it, right? Now we just have to return the rounded bag, and we need to look at the value we want, which is capacity, right? And so what this function will return, right, it will not return the ideal combination of products. If we wanted to do that, we would have to do some backtracking. I think it doesn't really fit the length of this tutorial if we were to implement that too. So what this does return is the basically optimal value or profit that we can actually get with this problem. And so we can use this optimum value to check whether our greedy strategies actually worked. Okay, now let's print this value. And let's see, right? Let's see if one of our algorithms is actually optimal. And so if we look at the output, right, we can see that 40 is actually the optimal value for this problem. So 40 is the optimal profit. And we can see that our greedy strategy achieved this value. So it did find the optimal value in this case, right? It doesn't mean that it will always do that, but for this specific case, it did. So I hope you did learn something from this, and we're almost done. I want to discuss one last basically theoretical subtlety of these knapsack problems. But basically to recap, we have made two methods, basically two greedy algorithms, and we have checked whether one of these or both actually were optimal using a dynamic programming method. And it's also possible to use this method to return basically the fruits you should select. That requires some more code to be added in. So let's now switch back to the PowerPoint about dominance relations. And so what dominance relations are relations that can actually be used to make this problem a lot easier. And so it's basically just, we need to look at this problem, we need to think in a bit of a smart way. And so when we look at this, and I were to say, for example, I want to find the optimal solution, we're just going to use this table and our brain. We're not going to use any programming technique. Let's say somebody says, well, I think pomelo is going to be inside the optimal solution, right? Pomelo has this weight of 1,500 and has a profit of 8, right? Then we could actually just tell this person that, pomelo sadly won't be there. And, you don't have to do any computation whatsoever because this is what is called a dominance relation, right? I can actually show that there is a alternative fruit that we could always take that is better, right? And so it would be very simple, this argument. Let's say that pomelo is hypothetically in our optimal selection of fruits. Well, then what I would do, I just take this pomelo and replace it with a durian. And when I've done that, right, the weight remains the same. So there's no problem there. We will not have a problem with the capacity. But as you can see, 22 is clearly larger than 8. So we have got an improvement in our profit. So pomelo will never be part of the optimal solution, right? So it can basically be crossed out like that because it will never be part of the optimal solution. You know, what makes this like great is the fact that you have actually reduced the possible amount, basically the combinations that your problem could actually take. And this will make it a lot easier to solve the problem. So this would basically be the end of this video on knapsack problems. And I hope to have given you a better understanding of this topic. Giving you a few approximation strategies and also a quick dynamic programming method. If you enjoyed the video, consider, subscribing to this channel. I will be producing more of these type of videos on programming, on algorithms, and maybe also drop a like or drop a comment if you have a question or if you think that there's something, I could improve. That's always welcome. I really appreciate that. And, maybe see you in the next video.